Hi class, today we are going over the slope of the tangent and instantaneous rate of change and completing this note. So prior to watching this video, you should have completed the investigation and watched the video where I take up the investigation, as well as another little display or demonstration I have for you there. So by now, I think you've determined that we're going to describe the connections between the instantaneous rate of change and the slope of a tangent, and then make connections between that and secants approaching the tangent. So we're going to be able to actually use limits now to do this, whereas in advanced functions, we were using estimations. So the first bit of this will be a bit of a review, this graph, and then we get into the definition using a limit. So if we take a point P, so you can draw a curve, you can see I kind of made a shallow quadratic there. So you can take a point P and you can draw, let's do a line here. So this is the one downfall of doing it in Word because I can't get this quite perfect. But please actually do use a ruler on your paper and draw a tangent to P. That's really straight. Okay, so this is a tangent. So a tangent only touches the curve at one point, at least locally. Okay, so the idea here is that if we take a series of secant lines that slide closer and closer to the point P, our secant lines will become closer and closer to approximating a tangent. So we think about Q, these secants. We think about Q as sliding closer and closer to P. So as Q slides closer and closer to P, these red secants approximate the slope of a tangent. So we can say, remember, that the slope is delta y over delta x. So that is whatever our f at x plus h is minus f at x divided by h. So that's the difference quotient that we learned back in advanced functions. But now we can define this using limits. So the slope of a tangent to a function y equals f at x at point A, f at A is actually, the slope is actually the limit as the change in x approaches 0 of delta y over delta x. So we want this change in x, so the distance between P and Q, to approach 0, to become so infinitesimally close to 0 that it's practically there without actually being there, because if it actually was there, we couldn't evaluate it. So this is the same thing as saying the limit as h approaches 0 of the difference quotient. Sorry, let's just say f at A plus h minus f at A all over h. And then we can say if the limit exists. So think about it. We can't actually plug and chug h equals 0, so that should be an arrow, h approaches 0. We can't actually just substitute 0 in because that would result in division by 0, which is not allowed. But we can find the limit with all of the different techniques we've already been discovering in our evaluation of limits. So basically, the slope of the tangent is the limit as h approaches 0. H gets closer and closer, so in other words, the secant becomes infinitesimally close to the tangent so that it actually basically becomes the tangent, is the concept. So let's go and actually find some slopes of tangents now without having to estimate them. Yay, this is so much more exciting than advanced functions. So our slope then is the limit as h approaches 0. Okay, so it's this function, just x squared at 3, 9. So we're going to take f at 3 plus h, subtract f at 3, and divide that by h. So let's remember what this means. We're taking a point that's just h past 3, where h is approaching 0, and then dividing it technically by 3 plus h minus 3, which just reduces to h. So remember, this is just your typical slope formula. This is just y2 minus y1 over x2 minus x1 with a limit attached to it. So let's not forget our limit statement. That is, I will admit, my #1 mistake. I forget it all the time, but you can't. Okay, so now we sub 3 plus h into the function. So you get 3 plus h quantity squared minus 3 squared all over h. So now we expand and simplify. So you get h squared plus 6h plus 9, and then minus 9 all over h. So watch what happens. Oh, I hope this isn't behind my head. Okay, so then you get the limit as h approaches 0. Okay, check this out. So 9 minus 9 goes away, and so then on the top you can common factor out an h. So this is where the fun comes in. Bang, bang, these go away, and then we can let h approach 0. So we get that the answer to this is 6. Cool. Okay, so we don't have to approximate, we don't have to estimate. We know that this limit is 6, and so therefore we know that if we were to draw x squared and to throw in a tangent, it would be 6. Okay, the slope of that tangent would be 6. So visually, let's see what that looks like. I should have had Desmos set up. Sorry, guys. So you can go to Desmos, graph the function f at x equals x squared. Okay, so we're looking at the point 3, 9, which is here. Okay, so if we are to draw a tangent at 3, 9, won't let me do that, huh? GeoGebra lets me do that. So if we were to draw a tangent there, we would get a slope of 6. So hopefully that you guys can actually visualize that. So at 3, 9, if we were to draw a straight line right through that point there, a tangent, the slope of that line, the slope of that tangent would be 6. Okay, I just wanted you to have an understanding visually of what that meant. Okay, so what about here? Find the slope of the tangent to this curve at x equals 3 and its equation. So let's just graph this function just for fun, just to kind of see what we think it might be. So we get negative x squared plus 4x plus 1. Okay, so here's our function. And the question says that we want the slope of the tangent at 3. So we can see that the curve here at 3 is going to be equal to 4. So tangent here then is going to have a negative slope. It just kind of helps to visualize so that we understand our answer and can interpret it within the context. Okay, so let's go back and actually do this because it's kind of fun, right? I mean, you guys would do this on a Friday night at a party. Find some limits. It's all good. All right, so it's the limit as h approaches 0 of, so we're going to put in 3 plus h in for x. So negative bracket 3 plus h bracket squared plus 4, 3 plus h plus 1. Okay, and I'm going to change to a different color because now we're going to subtract in big brackets here, actually putting 3 into this function. So negative 3 squared plus 4 times 3 plus 1. Okay, so the green is the function evaluated at 3, and the blue is the function evaluated at 3 plus h, and we divide it all by h. So we get the limit as h approaches 0. Okay, so watch what happens here. So we would get negative h squared plus 6h plus 9. Then we'd make that all negative. Then distribute the 4, so you get 12 plus 4h, and then the 1. So all of that gets me to negative h Well, I guess I should actually show this to you. Okay, I'll actually show this to you. I had it really shortened out, but I'll do this for you. So you get h squared plus 6h plus 9, all made negative, plus 12 plus 4h plus 1. And I believe that you'll believe me that this is all minus 4. So all of this green becomes 4 if you actually go and find it. All divided by h. Okay, so the limit as h approaches 0. Okay, so you get negative h squared. Okay, so then you get minus 6h plus 4h. So minus 6h plus 4h gives us plus 2h. Okay, and then you get minus 9 plus 12 is 3, plus 1 is 4, minus 4 is 0. So you're actually just left with that. So then you can take the limit as h approaches 0, take out an h, you're left with negative h plus 2. Sorry, negative h minus 2. If I'm taking out an h. What am I doing wrong here? Oh, this should have been minus 2h. There we go. Minus 2h because I have a minus 6 plus a 4. So minus 2 all over h. These cancel out. This goes to 0. So you get that your slope is negative 2. Yay! Okay, which sounds right. So the slope of my line is negative 2. Okay, but it asked me for the equation of the tangent as well. So the equation will be y equals minus 2x plus b. And now I can just sub in the point 3, 4 and solve for b. So 4 equals minus 2 times 3 plus b. So b equals 10. And my equation is y equals minus 2x plus 10. Okay, so I can go back and actually graph that. Y equals minus 2x plus 10. And look at that beautiful tangent. There it is. So it touches the curve at 3, 4. What a glorious sight to see. Okay, example 3. Find the slope of the tangent. So now we have a square root function. So this might seem daunting, but we know how to deal with limits and square roots. We've done it before. So the slope then is going to be the limit as h approaches 0 of the difference quotient. So we're going to put the root of 9 plus h, okay, since we're evaluating it at x equals 9, minus the root of 9, all divided by h. Okay, so we can simplify this to the limit as h approaches 0 of root 9 plus h minus 3 all over h. Now be careful, some students are tempted here to simplify this root and take out a root 9 and a root h. So they would put 3 plus root h. You can't do that, okay? You cannot, because it's addition, so you can't simplify that way. So we dealt with limits like this before. What do you do when you have a limit with a square root in it? You multiply by the conjugate. So the conjugate here is root 9 plus h minus 3. Plus 3. And you do that to the top and the bottom so that you're just multiplying, in essence, by 1. Okay. So when you expand this out, you get 9 plus h, minus 9 all over h bracket root 9 plus h plus 3. Okay, so look what happens on the top. You get 9 minus 9, they cross off, and this h are going to cross off. Okay, so then you get the limit as h approaches 0 of 1 all over root 9 plus h plus 3. So now h approaches 0, so you get 1 over 6 as your final answer, because root 9 is 3, 3 plus 3 is 6. So the slope of the tangent there is 1 over 6. Okay, you can graph it on GeoGebra and check that out, or Desmos, whatever you prefer, and you will see that that is correct. Okay, you would have a rise of 1 for a run of 6 if you drew a tangent there. Okay, so example 4. Determine the slope of this rational function, 3x plus 6 over x at the point 2, 6. So this is nice because they give you f at 2 and you don't actually have to find it yourself. So you know now that f at 2 is 6. So again, you just start with your handy, sorry, I should put m equals. You just start with your handy limit statement and you're putting in 2 plus h in for x at the first part. So you get 3 bracket 2 plus h plus 6 all over 2 plus h. Remember, you have to put in a 2 plus h for all the x's. Minus 6, okay, because we know f at 2 is 6. Okay, and then we divide that all by h. Okay, so now what are we going to do with this? Well, don't freak out. You just got to trust yourself that you can do this. So expand the top. You get 6 plus 3h plus 6 all over 2 plus h minus 6. And I'm just going to put that in brackets and multiply it by 1 over h instead of just making it look like some huge division, just because I think this looks nicer. So dividing by h is the same thing as multiplying by 1 over h. Okay, so now this gets me 3h plus 12 over 2 plus h. Okay, but I want to get a common denominator, right? If I have a fraction and plus a constant, I want to get a common denominator. So my common denominator is 2 plus h. So I have to multiply this 6 by 2 plus h. So minus 6 bracket 2 plus h. And then all of this goes over 2 plus h. And that's all being multiplied by 1 over h. Okay, so now we simplify. So 3h, notice we're going to be doing minus 6h, gives us a negative 3h. And then you're going to get a 12 minus 6 times 2, so 12 minus 12, so that goes away actually. So we get negative 3h over 2 plus h times 1 over h. So look what happens. Now we get a slice and dice. Okay, so these cross off. And so now we can just let this go to 0. So you get negative 3 over 2. So the slope of the tangent to this rational function at this point is minus a half. So fun. That's the slope of the tangent, people. Okay, here's one for you to practice. Are you actually going to do it? Are you going to come to class tomorrow with it done? I hope you are, because it's a good little practice for you. It's not too bad. So try that. It's super fun. So pause the video, do it. All right. Then I just have 2 more examples that you can go watch some Netflix. Okay. Watch. People will be watching this video like 8 years in the future, and there's not even going to be Netflix anymore. It's going to be so embarrassing. All right, so remember, the slope of the tangent can also represent instantaneous rate of change, which is defined as how the dependent variable changes with respect to the independent variable at any instant. So instantaneous velocity is the change in position with respect to the change in time at an instant. So if we have the height of a rocket, and it's modeled by this function, we can find its instantaneous velocity now wherever we want using limits. So we could say that its velocity is equal to the limit as h approaches 0 of, okay, so we're going to put 4 plus h in for all the t's. So minus 5 bracket 4 plus h plus 30 bracket 4 plus h. Oops, I forgot the squared. 4 plus h plus 2 minus, okay, minus 5 times 4 squared plus 30 times 4 plus 2. So you actually have to go find that. and divide it all by h. Okay, so I'm going to challenge you guys to actually finish that and solve it. You should get that your final answer is negative 10. Okay, so when you go through and solve this, you get negative 10. Please actually do it. Make sure you get that. So we have to be able to interpret that now within a context. So notice that S was in meters and T was in second. So this is meters per second. So the negative is interpreted as the rocket going down, and the 10 is interpreted as the speed. So we can say the rocket is moving down at a speed of 10 meters per second. All right, there we go. All right, and finally, you can have something like this, okay? The total cost in dollars of manufacturing X calculators is given by this cost function. And notice it has a root in it. What is the rate of change in the total cost with respect to the number of calculators being produced when X is equal to 100? So that's the same as the slope of the tangent. So we just do our rate of change formula that we've been doing. So the limit as h approaches 0 of 10, and then we take root 100 plus h plus 1,000. And then subtract, what do you get? So 10 root 100 plus 1,000. Okay, and then divide it all by h. Okay, so you get the limit as h approaches 0 of 10. Now remember, I can't simplify that. I gotta leave it how it is, as annoying as it is. Okay, and then this becomes 10 times 10, which is 100. Sorry, 1,000. Sorry, 100. 10 times 10. So this becomes minus 1,100. Okay, all divided by h. Okay, so now we need to multiply by the conjugate since we have a square root. So that indicates that we need to use the conjugate. But first we can simplify this 1,000 minus 1,100 to make our job a little bit easier before we use the conjugate. There's actually one more step we can do here. So you get 10 root 100 plus h minus 100 all over h. So we're going to multiply that now by 10 root 100 plus h plus 100 all over 10 root 100 plus h plus 100. Okay, so I'm going to have you guys actually go and solve that because I know you can. And see, check in with me tomorrow and we'll see if you guys got the right answer. All right, read over the success criteria and make sure that you can interpret this answer within the context. Remember, this is going to be the cost per calculator. It's the rate of change because C is in cost and X is in number of calculators. So whatever you get here is going to be the increment